Okay. Yeah. Okay, so we saw we have seen so far what are the operations on quantum states, and then we saw measurements. Okay, and yeah, so let's recall and then calibration. This is better. So we have seen like the general ones. So which is like first attach. That's okay, initialized to 0. Then after that, perform limited. System. Trace out. That's it. Okay. So you can already see an important operation is just unitary, like so important operations. Unitary. And the second one was measurement. And then, of course, I mean, there are other ones which we do without thinking, like just attaching an ancilla initialized to any fixed state. That would be a quantum operation, or just trace out part of it. So let me, before going ahead with the next topic that comes after this, so let me just show you, going back to the classical scenario, how this is an extension of the classical notion of a public coin, of a private coin. Sorry. Yeah. So remember when we are looking at private coin. What happened? Did I just get disconnected?
Yeah.
Hello. Yeah. Did you hear the earlier thing, or was the audio missed?
No, it was clear.
It was clear. Okay. No, because somebody is reconnected from. No, it's Aditya joined. But somehow the Zoom reconnected, so there was some problem. Okay. Anyway.
Oh, okay.
Okay, yeah. No, the sharing stopped. So that was the problem. Okay. So in the private coin algorithm, remember, like what we did was like, so things were similar, except the very first step was attach and ancilla. Okay, initialized to. So there was the 0, which is the workspace. Okay. And then This was the private coin. Okay. So some bits tossed, let us say, heads, tails. So some bits tossed uniformly and independent of everything else. So I want to say that in the quantum setting, this definition, this definition seems to be stronger than what I wrote out here. I will show you that in the quantum setting, this definition would not be stronger. And this is because of the following thing. Okay. So why? Quantum. Okay. Simulate. So that is because of the following reason. So let us say there is some workspace. Okay. So there are some bits X. Okay. And now I want to simulate a private coin on a certain number of bits. Okay. Let us say, let me start off with one bit. Okay. And the procedure is similar for the others. So start off with. Windows interface. So let us say just a 1. So I want to simulate 1. Okay. So I'll set up a circuitry like this. So I'll pass this through a unitary operation. So I start off with whatever bits I have, let's say the vector X notation, and I've attached ancilla. So this is the ancilla. Then remember I said
you're generating uniformly random bits then, right?
I want to simulate one uniformly random bit.
Okay.
By attaching only ancilla initialized to 0. Okay. So I have put in one ancilla initialized to 0. I pass it through a gate which is called the unitary transformation, called the Hadamard gate. Then let us say, yeah. So maybe this was your doubt, Shanti? I don't know. So,
yeah, I mean, I saw the gate and I understood you must be wanting uniformly random.
Yeah. So just hold your horses. So I'll draw the circuit diagram and explain what these things are. And after this, it is the rest of the algorithm. So I want to simulate one random bit, but you can see that finally I have used 2 ancilla bits, but both are initialized to 0. Okay. So what this does, let me this will keep doing whatever it does. This bit or this bit is not touched henceforth. So it just remains hanging like that. So let me write down what the gates are. So remember the Hadamard is the unitary operation acting on one quantum bit. So one quantum bit is a 2-dimensional system. So it's a 2x2 unitary matrix. So I just have to say what is its description in terms of the standard basis. So remember, like, I mean, the first column corresponds to the action of the unitary on the first standard unit vector, which I call KED0, which is 1, 0. And then the second column is the action of unitary H on the second standard vector, which is 0, 1. which I'm calling cat 1. So this is the definition of the unitary. Okay. And the second one, okay, so this is denoted by this fancy symbol. This is actually, you can see unitary which is acting on 2 qubits. So this is 1 qubit, this is 1 qubit. And of course, the output space is the same dimension, output space is also 2 qubits. So let me see.
Pranab, haven't you drawn the symbols upside down? As in, the control should be the bottom and the operation should be top, right?
It will not matter.
Oh.
So this is something called a control knot, C knot for short. Okay. So now, remember it's a unitary which acts on 2 qubits. So 2 qubits means the vector space is C2 tensor C2. Okay. So it's a 4-dimensional vector space, C2 tensor C2, and for tensor product spaces, we know how to write the tensor basis. So we take the computational basis of the first guy, computational basis of the second guy, and we form this pairs with the tensor product symbol. And we know how to write it in shorthand. So 0, 0, 0, 1. Action on 1, 0, 1, 1. Okay. And let me just remind you, 0, 0 by definition is shorthand for 0 tensor 0, okay, which is equal to, remember 0 is the first standard vector. And this, if you recall, the way we do it is we stick the second vector and multiply it by the vector entry coming from the first vector. So 0, 1, 0. And this, to cut a long story short, is this. So this is what I would naturally call the first standard vector if I'm doing lexicographic order. Just to show you, let's say maybe 1, 0. So this is 1, 0. So this is 0, 1, tensor 1, 0. And you can check that this will be the third standard vector. So actually the tensor product basis, tensor product of the computational basis respects a lexicographic ordering that you would normally give. And I mean, though this is like kind of new notation, it's really, I mean, this is the third column and this is really the third standard basis vector. So is it clear that the ordering is just the standard thing that we would do anyway? Okay, so let me write down what is this matrix. So what it does is it sends 0, 0 to 0, 0, okay, 0, 1 to 0, 1. Okay. Then, so what is this? Okay, so I mean, then the name control knot becomes clear. The first bit is the first wire is treated as the control bit. And the second wire, the second bit is treated as the target bit. So control knot says that do a NOT operation on the target bit, provided the control bit is 1. If the control bit is 0, do identity, that is do nothing. So when the control bit is 0, that is the first bit is 0, I'm doing identity, okay, on the second bit. So you can see the identity matrix here. And if the control bit is 1, do a NOT. So what is NOT? NOT means if the second bit is 0, it goes to 1. Okay, so here
maybe like labeling the rows will make things.
Yeah, it's the same labeling. The same labeling. So you can see the input 1, 0 goes to 1, 1. So the control bit is 1. I do a NOT on the second bit goes from 0 to 1. And similarly, the input 1, 1 goes to 1, 0. Okay, control bit is 1. the control bit is 1. So I do a not on the second bit. Second bit goes from 1 to 0. So this is the overall unitary matrix. In fact, you can see it's a permutation matrix, right? It's a matrix which has exactly a single one in every row and every column. So this is the control knot, and I mean, even more explicitly, you can remind yourself. So what does C naught do? So it maps. Let's say I started off with the bits A comma B. It maps it to A and A XOR B. You can even check this. So A is the control bit. Okay, so this is the control knot operation. So I've described what is there in this circuitry. Let's run through it and see that it does what we claim it does. So what happens? Let us run through this. So let us say I start off with X 0 0. That's what I start off with. Then there was a Hadamard which sends it to X, and you can check that this goes to 0 plus 1 by that is the Hadamard. Okay, so let me show this. So what does cat 0 go to? This one. So this is nothing but cat 0 plus cat 1 by root 2, and then it's I think better to write the tensor product symbols now. And now, after the control knot, this will go to X. You can already see that this is a familiar state. This is my EPR pair. The example of the entangled state which I had given a few lectures back. So I land up with this, and then the prescription says that after this, rest of the algorithm. So now you say, okay, rest of the algorithm, I mean, this looks so simple. I mean, does it really work? So one way to convince yourself that it works is the following. So for the rest of the algorithm does not care about the last bit out here. It only cares about X and this, the first bit out here. Okay, so let us look at the reduced state on the first 2 bits. In other words, let us look at the marginal or the density matrix. So what I'm going to do out here is just to emphasize that we are not going to consider this anymore. This is the symbol, the ground symbol is, I'm just tracing it out. I'm discarding this bit. So if I discard this bit, what does this look like? So now I cannot think of it as a vector anymore. I have to start thinking of density matrices. Okay. So first of all, what does this look like in density matrices? So in the density matrix language, these are ket vectors, column vectors. I'll have to multiply it by bra vectors, okay, which is a conjugate transpose row vector. So you can check that this will just become this. Okay. And now I have to tell you what this looks like. So this will be just multiply.
Pranab, the second term is ket 0 0 bra 1 1. Not 0 1.
Correct. This one. Yeah. So So this is what I come down to. Okay. Yeah. So implicitly I used things like I mean, just to remind you, I mean, it's something that you've already seen, but maybe it's worth it. So remember, like if I have something like cat X bra Y, this is actually a product of matrices. This is some n by 1 matrix, right? This is n by 1, and this will be some, it's a 1 by n matrix. So the product is n by n matrix. It's a rank 1 matrix. And if I have something like X1 tensor X2, which is exactly what I have wrote here. This is my X1, this is my X2. So I have this X1 tensor X2, and now I multiply it by, when I do the, let us say I took the bra of the Y's. So again, you can check, for example, that like if I have Y1, some vector Y1, Y2, may not even be basis vectors. Like if I do the conjugate transpose of this, the conjugate transpose respects the tensor product. So Y1, it's Y2. So now I'm using the property of matrix multiplication under the Kronecker product. So this is equal to X1 Y1. So this is a certain matrix tensor X2. Okay, so it is this that I actually used out here. So this one was X1 cat X1 bra Y1, and this is cat X2 times bra Y2. Okay. Happens that X2 is equal to Y2, and then I expand things over. Okay, this is just distributivity of matrix multiplication, right? So again, just to remind you, nothing beyond normal. Like all I'm doing is that A plus B times C plus D. It's AC plus AD plus BC plus BD. I just have to respect the order, okay, because matrix multiplication doesn't come. So I've used all that and opened it up. Is this clear? Yeah. Hari, is this clear?
Yeah.
Okay, good. Good. Yeah. So now I'm going to trace out. Okay, so this is trace out last. So remember when I'm tracing out, I was just take like it's very easy to do once things are in expanded form like this. I just take the usual trace operation, the last bit. Okay. So for the last bit out here, this is cat 0 bra 0. Okay. So again, let's come down. So again, of course, I'll be using things like this is same as and similarly, let's do one more term 0 0 1 1. This is the same as 0 1. So to remind you, this was 0 tensor 0, just a shorthand for that. This one was bra 0 tensor bra 0. Okay. And I'm again using this thing out here to conclude this. So once I write things this way, to do the partial trace, I'll just apply the trace operator out here, trace here, okay. But then the trace of, so now if I would just do trace last bit. So in the first case, the trace was 1. In the second case, the times 1. In the second case, it is times the scalar C. Recall that cat 0 bra 0 is this matrix. And get 0 bra 1, you can check is this matrix. That. I mean, one way to see this quickly is what is this get bra doing? Okay, so so if you multiply by some vector on the right, okay, it is basically projecting it to the cat 0 component, and that will give a scalar. Okay, and that scalar will go and multiply the vector out here, which is cat 0. So, so if I supply cat 0 on the right, then the output is cat 0. Like bra 0, cat 0 is 1. The inner product of these two is 1. Okay, so the scalar is 1. So scalar 1 times the vector cat 0 is the vector cat 0. So I know that this operator sends cat 0 to cat 0 and cat 1 to the 0 vector. And this is exactly what is being done. Cat 0, the 0th standard basis vector is going to itself. The first standard basis vector is going to the 0 vector. For this guy, this is cat 0 bra 1. So what is this doing? The second standard basis vector is going to the first standard basis vector. So I have a 1 0 out here. And the first standard basis vector, okay, so bra 1 times cat 0 is 0. Okay, so the first standard basis vector is going to the all 0 vector. So now you can see that the trace of this matrix is 1, the trace of this matrix is 0. And that's exactly what I came up with out here. So trace with 1 and 0. So now you can see easily see that you can evaluate this. So x remains the same. And now what do you have out here? So cat 0 0 bra 0 0 on trace out will just give me cat 0 bra 0. Now let's
by 2 by 2.
So this one will give me cat 0 bra 0. This is cat 0 0 bra 1 1, okay, which you have done out here. On trace out, it gives me the 0 matrix, 0 operator. So nothing from here. Similarly, cat 1 1 bra 0 0, trace out the last bit will give me the 0 operator. Only cat 1 1 bra 1 1, trace out the last operator, trace out the last bit will give me cat 1 by 2. So this is what I get. So I get the density matrix, which is cat x bra x, tensor a density matrix which looks like cat 0 bra 0 plus cat 1 bra 1 divided by 2. But then what is this matrix? So this is something very familiar. So this is it's actually the identity matrix. Right. Cat 0 bra 0, we already saw the matrix somewhere. It is this matrix. Cat 1 bra 1 will be the corresponding matrix, but now there will be 1 in the 2 2 position. So when you add it up, you will get the identity matrix. It's the identity matrix and half. So what does this mean mathematically? It means that the initial work bits are the same out here. Okay, and in tensor product of them, attached to them is one bit, which is in the state 0 with probability half and the state 1 with probability half. So this is the private coin. So this is the form private. So what has this shown me? This has shown me that if I want to simulate one random bit, okay, one private coin out here, I can do it in quantum. So attach twice the number. In this case, like attach 2 ancilla bits, both initialized to all zeros. Append this circuitry, okay, and then ignore the second half of the bits. Place it on. So the first half of the bits after this will behave like uniformly random bits, and then anyway in tensor to the input bit sets. So the rest of the algorithm works as well as the classical case. Okay, the rest of the algorithm, what the rest of the algorithm sees here is that there is X here, and then there's a uniformly random bit. Okay. So is this calculation clear? Yeah. Okay. Good. So let's proceed now. Yeah. So now, that I've convinced you that classical randomized algorithms, private kernel algorithms are a special case quantum algorithms. Okay, there's one more part, but that we have seen some part of it already. So remember when we were thinking of
There is
classical.
there is just one subtle point which I would like to point out. So, I mean, yeah, you have access to the private coins in the form of the maximally mixed state. That is true. But to get an answer from the algorithm, you have to condition on the outcome of that ancillary register, and that is the measurement part that you did not show in the algorithm description. So at some point you would have to measure and observe, which is essentially conditioning, and that will give you the random bit and the part of the algorithm which the quantum circuit did with that realization of the private coin. The other thing just goes away, it collapses away. So I mean that is
no, I think, I mean, no, so there are two different parts, and I think I mean one of them is not necessary. So as far as simulating one random bit is concerned, we have done it. I mean, I don't care what is whether you measure it or not. The rest of the algorithm is not going to look at this anymore. Okay. So we don't have to bother about this.
No, but definition.
Now, if you want to now you can say, wow, I want to read out the answer. Like, okay, the rest of the algorithm does the computation, read out the answer. So yeah, I mean, you have to measure the so-called answer bits out there. But what I should now maybe emphasize is that like if you're trying to simulate classical into quantum, then the rest of the algorithm is classical. But what type of classical algorithm it is? Okay. So remember when we were doing the data processing inequality, I said it's a classical reversible algorithm. Okay, classical reversible algorithm is just a permutation of bit strings. So it's a unitary operation, okay, because it's a permutation matrix, and that's it. So it fits into our unitary model, and we just stick it out. So, and anyway, because this algorithm is classical, whether you measure or not is kind of a formality.
No, not really, right? I mean, the definition of simulating a random bit is the following: that there exists an algorithm A such that on pressing a button, this algorithm gives you a bit B such that probability B equal to 1 is equal to half. So,
yeah, so I have already done that. So the only truly quantum part is this one, the Hadamard and control node.
Where is the bit coming out? That's my question.
This is the bit.
This is the bit, but that bit is in superposition, no? That's my
question.
That
bit is entangled with this, right? It's in EPR state, so its reduced state is just a random bit. This is how the all this quantum random number generators operate.
So you're saying that you don't need the measurement to like.
I don't need any measurement. So I mean, if you recall what we did in quantum algorithms, what I've essentially done without telling you the jargon is the principle of deferred measurement. So you don't have to measure. I mean, if you're doing enough control nodes with fresh ancillars initialized to 0 like this, you can wish away all measurements.
So deferred measurement is just that what you were saying earlier.
Yeah,
at
just
the
this.
end.
Yeah, it's basically this.
Okay.
I mean, deferred measurement is applied more generally in the sense that there even the rest of the algorithm, let us say, is quantum, and somebody described a quantum algorithm which does unitary operations, then measurements, then some more unitary, some more measurements. I don't want that. I just want one unitary operation and maybe one measurement at the end to read out. So deferred measurement says that all the intermediate measurements can be removed by putting in fresh ancilla bits here, doing control knots, okay? And then at the end, you just measure the output system. That's it.
Okay, okay, yeah, that makes sense. That makes sense.
Yeah. So this additional stuff you never have to measure. They are really, I mean, discarded. I mean, it goes to the earth, grounded. So more questions about this translation?
So when we use the zero ancilla, which is not random, we are getting a random bit at the output with the Hadamard block.
Yeah, so the random bit is here. So
yeah. So where's the randomness in the Hadamard block coming from?
No, so I mean, if you look at the mathematics, I mean, this is like equal amplitude on zero, right? I mean, if I put in ket0 out here, I get a superposition of ket0 and 1, and it's a uniform superposition. The same amplitudes are there.
Okay.
So it's kind of the uniform randomness is coming from there. But there's a difference between randomness and superposition. So right now, this is superposition. This is really sum of two vectors in the Hilbert space. Okay. If I did not add the second zero and do the control knot, then I could not have said that this is a random bit. Then it would have been a quantum bit. So if I had not done this, then wipe it out. So right now this is a random bit. Okay. But if I had not done this, then what would I have got? I would have got something which would have looked like X.
You would have gotten a pure state pure state essentially.
I would have got this vector. Okay.
Yes.
And then you convert it to density matrix. So if I convert it to density matrix X, and then see how different it looks. So convert this to density matrix. So I would have got this. And look at what I got for the reduced state, which is just 0, 0 plus 1, 1 by 2. Whereas if I had not just kept the Hadamard here, not done the control knot and the rest of the circuitry, this is not 0, 0 plus 1, 1. There are these two cross terms also, 0, 1 and 1, 0. Okay. And they are just different quantum states. Their effects are completely different. Does that give you some further understanding?
Yeah.
So yeah, so the second ancilla and this control knot is important, or else you'll be stuck with something like this, and this is not what you want for the private coin. What I want for the private coin is this. Yeah, good.
I mean, as you said, you could have measured it, but you don't want so many measurement circuits in the middle. So this is much more elegant, this way of doing things.
Yeah, and also I want to fit it into a model. I want to say that a general quantum operation is just this: attach an ancilla initialize to 0, perform a unitary or joint system, trace out ancilla. So that's it.
Right. Okay.
So these are my input bits X. I attach this ancilla 0, 0. This whole thing is the joint unitary now. Okay, and then I trace out. This is what I trace out. And if fine, I mean, if I only interested in some of these bits as answer bits, you can say I trace out everything. That doesn't matter. That's it. Yeah. So everything else with intermediate operations, etc. I mean, which can be like translated into this paradigm. And I said measurement, like, okay, unitary you can clearly see is just the second thing. Even measurement, as I defined, can actually be translated in this paradigm. That attach an ancilla, perform unitary, and trace out ancilla. And you can sort of see it out here. I mean, so the basic idea is the same. That as Shantan was saying that, like, I could have added one ancilla, done a Hadamard, and done a measurement out here. If I did a measurement, sure. I mean, I'm in the state cat0 plus cat1 by square root 2. It's a superposition state. Okay, it is not a random bit, but if I measure it, I get a random bit, which is the classical 0 with probability half and the classical 1 with probability half. But instead of measurement, I can attach one more ancilla bit, do a unitary operation. Here it's the control knot, and then trace out the same effect. So this should give you some confidence that even measurements can actually be converted to this general format. I don't want to, get into formal proof of that because it's, we'll get into it if something, really requires it later. But I want to go ahead with the information here. So far, we have been just building up the quantum computation model. But this is a good point to ask more questions.
I have a notational question. So I have seen this notation before in Aditya's slides, the grounding. Does that just mean trace out?
That's just trace out.
Okay.
Okay. So let's go ahead. Okay. So now we're going to an important topic, which is distance quantum states. So general quantum state, remember, we are modeling it as density matrix. So slowly we're getting into information here now. Okay. So remember, classically we had a notion of distance between two probability distributions. So our favorite distance was the L1 distance. So I had a probability distribution. So these are like distribution on the same space X. And remember, this was defined as the L1 norm. So sum over sample points X, Px minus Ux. Now we want to, so the notation will be the same, but I have to define what it means. So I have a density matrix.
There a half somewhere. Oh, that's total variation. Okay, total variation is half of L1.
Yeah, I don't want to put factors of half because sometimes you forget that half was there, not there.
No, I get confused. Yeah, I also get confused. That's why I asked.
Yeah, so it's best not to put factors. Okay, so what Shantan is saying is that many guys like to put a factor of half. People like to put a factor of half out here because you see, if the two probability distributions, what is the maximum L1 distance between them? That is 2. That happens if the supports are disjoint. Okay. And then some people don't like the maximum distance to be 2. They want the maximum distance to be 1. So they put a factor of half out. So we'll not do that because, if you write formulas assuming half, sometimes you forget that there was a half when you read something else. And yeah. So we will live with the fact that the maximum distance is 2. Similarly, when we are doing distance between density matrices, we live with the fact that if the quantum states have disjoint support, okay, or well, the analog of disjoint support, orthogonal support, then the L1 distance that I'm about to define is going to be 2. Okay, so let me write down what is this. So these are density matrices on the same Hilbert space X. Okay. So remember, what is this? This is nothing but the vector. Yeah. So
I think that other definition, PA minus PB, where A is the largest set where P is greater than Q, that will help because that leads to.
we will talk of that characterization, but just wanted to do this. Yeah, this external does not interact well with Zoom on Windows. So I have to define it properly. So let us see. So this is okay. So rho minus sigma is a matrix. It's a mod x by mod x matrix. Mod x being the dimension of the inverse space x. So one way to define it. So let's just define it that way, and then we look at alternative characterization. So this is the sum of singular values of the matrix rho minus sigma. So basically, I'm defining a norm called the Shatton L1 norm. So that's the jargon of this. This is called the Shatton L1 norm. So in general, the Shatton norms are defined by you take a matrix, you look at its singular values, and you take the L1 or the L2 norm, whatever norm you want of that. So this is the definition. So this is the L1 norm of the singular values of the matrix rho minus sigma, which is singular values by definition taken a positive, so it's just the sum of singular values of rho minus sigma. So definition clear to everybody. Everybody knows singular values. Okay, good. But it's not clear that this is a norm of the matrix. Remember, like, so there's another name that we use a lot in the quantum computing literature for this norm. So this is also called the trace norm. And you'll see very soon why the word trace comes about.
I'm being very pedantic, but I just want to point out something. In papers, when they write trace norm, they have the half. So that's that. Yeah. So in papers and even in Mike and Ike, when they say trace norm, they have the half. I just wanted to point that out.
Again, depends on the authors. Some people do, some people don't.
Some people don't, even for trace norm.
Yeah. There are enough papers I've seen where they don't bother.
Oh.
Some of singular values are there. In general, it is a matrix norm. So for it to be a matrix norm, I mean, okay, so the question is why a norm matrices? So that is the question that strikes one immediately. So what do you mean by norm on matrices? So what are the properties of norm? First of all, it has to be greater than or equal to 0, which is fine. Sum of singular values greater than or equal to 0. Then it is 0 if and only if the matrix is 0. That's also fine, because if a matrix is non-zero, then it will have a non-zero singular value. Then you have the scalar multiplication. Like if I take some complex number alpha and I look at the norm of alpha m, it should be mod alpha times the norm of m. Okay, that again you can check from singular values. Like if you multiply a matrix by a scalar, the singular values get multiplied by mod of that scalar alpha. So that part is all fine. So the difficult thing is to show the triangle inequality. That I have matrices m and n. Why should the norm of m plus n be less than or equal to the norm of m plus the norm of n? Because the singular values of m plus n are not related in any nice fashion to the singular values of m or the singular values of n. You can definitely not say that the singular values of n plus n are the corresponding sums of the singular values of nothing like that. Yet it is true that this is the norm, and we'll see why. So we'll come up with alternate characterizations of this. So remember, m had the singular value decomposition. So let me write it down. Sum over I, so Si, and then so in our Ket-Bra notation, it will look like this, where let us say whatever it's some mod x dimensions, please. Some singular values are allowed to be 0. So this set AI so this is an orthonormal. This is an orthonormal basis, and similarly the other set BI. So these are the conjugate transpose, the bras of those vectors, but the original vectors are ket vectors. So this is also orthogonal. This is the singular value decomposition. Orthogonal. Yeah, and these are called the left singular vectors. The A's are the left singular vectors. The B's are the right singular vectors. In general, I mean AI and BI are different, but this is the thing. So this is a singular value decomposition. So everybody understands this. Right? So any matrix can be written in this form. And now, what am I telling? I'm just telling you that norm of, so this is defined to be summation over I. So that's what I'm telling you. That is what I would like to call the Schatten L1 norm. So what is this? Now, I'll say that the singular value decomposition gives me an alternate characterization. So what is that? Let us say, let's take a matrix M and multiply it by matrix U, a unitary U. And what is U? So I have to tell you what is U. So U is a matrix which sends BI to AI. So BI to AI. Okay. So you can check this is unitary, right? So because BI was an orthonormal basis. Okay. AI is another orthonormal basis. So it's just a linear map which sends one orthonormal basis to another. So by definition, it's a unitary map. Now, let us okay, so let us see what it does. BI, is that what I want? Okay, actually, what is the inverse? Okay, so the inverse of this will send AI to BI. It's also a unitary map. So what does this look like? So you can check. This looks like.
No, not inverse. UM instead of MU. Wait.
It looks like this, right?
No, that's not correct, right? I mean,
so why, let us see why is this. So so if I feed in A1, so U inverse will send A1 to B1, and M will send B1 to A1 times S1. And that's exactly what I do. A1 goes to A1 times S1. Similarly, A2, A3. See, to understand the action of this operator, I just have to study its action on the basis. I choose to study the action of the operator M inverse on the basis A1, A2, A3, dot. And this is what I did. Okay. So is this identity clear to everybody? So I have this, and now I can ask what is the trace of MU inverse? It is exactly summation I SI, which is equal to the one norm of M. I can even put a more out here. Okay. So why did I do all this? I said that, okay, I want to come up with an alternate characterization of the Schatten L1 norm. So start off with the matrix M I've shown that there is a unitary U, okay, such that trace of U inverse is equal to the one norm of M. Now, let's go ahead. So now, let us say I look at any other matrix MV inverse. And let us say what is V doing? V is sending to some orthonormal basis Ci. That's so this will be sum over I, Si, Ci. And now if I look at what is trace MV inverse model, so you can check that it is less than or equal to sum over I. So why is that? Let us see. So okay. So MV inverse, as you can see,
it's just triangle inequality.
Yeah, this is easy to check. I'm just doing it because I mean, one may not be used to this Canberra notation and all that. Okay, so it's a good notation once you get used to it. So MV inverse is this thing. This is the singular value decomposition of MV inverse. So the A's are the left singular vectors, C's are the right singular vectors. So far so good. But now if I try to find the trace, so let me try to find the trace. Okay, so I can say trace of MV inverse. So you just look at the diagonal elements in some basis. I choose to find the diagonal elements in the A1, A2, A3 basis. So what am I trying to say? I'm just trying to say this is sum over J. So what is this notation? This is saying take the matrix MV inverse, apply it to the vector ket AJ, okay, and then multiply that vector by the bra vector bra AJ. So what is this giving me? So look at let me look at the action of. Okay. So this is some vector. The MV inverse applied on AJ. Now, the moment I take multiplied by bra AJ, or in other words, I take the inner product, that means I'm finding what is the amplitude of this vector with respect to the AJth coordinate. So remember, my aim was to find the trace when the matrix is written in the AJ basis. Okay. And this is the AJ comma AJ, or let us say the J comma J entry of the matrix. Okay. How do you find the J comma J entry of the matrix? Applied on the Jth vector, in our case it's AJ. Okay. So you get something given by the Jth column, and this vector is a linear combination of the A1, A2, A3, so on. If I have to find out what is the coefficient in the Jth coordinate, I just multiply it by the bra AJ vector. Okay. So this is the J comma Jth entry of this. So now you can see this is summation J summation J. Summation. Right. So if I have AJ here and AI out here, remember they're orthogonal vectors. So this forces J is equal to I. The other cross terms will be 0. So taking j equal to eigen. And now I'm going to put mods. So mod. And now triangle equal to mod. So this is less than summation I si and then mod ci ai. And these are two unit vectors. Cauchy-Schwarz says that the inner product is at most 1. Okay, product of the length is at most 1. So this is less than summation. So I'm done. So what have I proved by this exercise? I have proved that the one norm of any matrix M is the maximum over unit trace V of trace of M. Yeah, I don't need the inverse. Is this clear? If I put an arbitrary V here, it is less than or equal to the one norm, and there is a certain V defined out here, defined by this fashion, in which case it is equal. So equality is indeed attained. So this is maximum. And this similar analysis will also say that this is maximum U trace U. You can do the same argument. So let me emphasize here, this is something very useful alternate characterization. Okay, is this clear to everybody? Okay, so now I want to prove that triangle inequality for this so-called one norm. Okay, that will complete the proof that this so-called this one norm is indeed a bona fide norm. So let us see. So I have M plus N, one norm. So this is equal to max P. It's a trace of M plus N P. And by triangle inequality, like so max trace of NV, trace of NV.
No, I mean, yeah.
And in particular, this is less than 1 norm. Okay, and in general, the inequality will be strict. And you can clearly see why, because the V which maximizes trace MV in general is different from the V that maximizes trace MV. So in general, this inequality will be strict, but then of course you can also see cases where it will be attained. I mean, if for some reason the same V maximizes the same, and same V maximizes M and N already tells you. So I know what is the V that maximizes this, right? I mean, the unitary is of this form. Okay, and if the same unitary U maximizes the expression for M and N, it basically means that right. So it basically
no. I don't think that logic is quite correct, and I'll tell you why. We have a candidate U which maximizes, but we don't know that there are no other U which.
That's true. Yeah, that's true. So I mean, yeah, I'm saying that if the same one maximizes, what does that tell you? That tells you something about the right singular vectors of M and N. That's all I wanted to say. Yeah, but yeah. So, but you are right. Of course, I mean, several V's could do it, but again, we know what are the V's that could do it. There is some redundancy in the choice of the right singular vectors. Okay, if two or more singular values are the same, then there is some redundancy. So because of the redundancy, there can be several unitaries that maximize the expression traceability. And yeah, so it turns out that like that redundancy can be exploited and can be something out here. Anyway, let's yeah. This was that was not a very sacrosanct statement. Our aim was to show the triangle inequality for n plus n, and we've shown that by this automatic factorization. So indeed, this is a norm. So what have we proved is this, any questions on this? Okay, let's in that case, yeah. Good. Yeah. So let's go ahead. And why were we doing all this? So actually, what we are going to do, as you may guess, is we're going to replace the notation has been built up that way. So in applications where we are looking at the L1 distance between two probability distributions, so there will be similar applications where the probability distributions are replaced by density matrices, and we look at the L1 distance between them in terms of shatter. Okay. Now, why is this interesting? Let us. So let us say let M be a measurement on X with, so X out here.
So you're doing Hellstrom's theorem now?
Yeah.
Okay.
What is this? I've never heard that name before.
That M be a measurement on H on the Hilbert space A, with classical outcomes. So I'll index them by X. So what do we mean by that? So M is given by this set of measurement operators. And let us say if I apply M on a density matrix rho in the Hilbert space H, okay, so then I will say that the probability of observing the outcome X. Okay. So we saw what how measurement operators are described. So the probability of observing the outcome X is trace of rho Mx. And remember what are the Mx's out here? So Mx's are positive semi-definite matrices. It's positive. Semi-definite, this notation, greater than or equal to 0, it's an abuse of notation. It just means positive semi-definite matrices. This is really the zero matrix of H. This is a matrix of H. And sum over X, Mx, is the identity of H. Okay, these are the measurement operators. So the probability of getting the exact classical outcome is trace of rho Mx. Okay, so now M is a measurement on H with classical outcomes indexed by the little x. Okay. Now, so let's define some notation. So,
Pranav, I just had a question to refresh one. So,
So M row is this vector.
Hello?
Okay. It's a vector, it's a probability vector over the classical outcomes that you get. So it's basically the entries will be trace of row mx.
Hello?
And I run over all the classical outcomes.
Hello? Hello?
And similarly, M sigma is the so it is the probability distribution I would get over the set X if the measurement M were applied to the state sigma. Right. So I mean, nothing mysterious. So this is the probability distribution that I get over the outcomes little x if the measurement M is applied on the state row. And if the same measurement M is applied on a different state sigma, of course, I get a different probability distribution on the set of outcomes. Set of outcomes will be the same, but the probability vector is different. And this is the problem. There was a question, someone?
Yeah. I had a question. So is it always necessary for the measurement operator to sort of store its outcome in a classical register?
Store its outcome?
As in, is it like this operator comes with some other register capital X where it stores the small x?
Yeah. So when you say measurement, the aim of a measurement is to get a classical output. So,
right.
So whenever we talk of a measurement, that X is together, the X is the classical output.
Oh, okay. So but there is, so then the operators are actually Kedra X M sub tensor M sub X.
Yes, yeah, you can think of it that way. I mean, this is if you want to keep track of what is the collapsed quantum state, okay, on H after the measurement. If you don't want to keep track of it, then you can say measurement is something that sends the Hilbert space H to the classical set X. Okay. It sends density matrices in H to probability distributions over X. And that's the view that I'm taking out here. So measurement M is applied on a density matrix, a quantum system in the Hilbert space H, but the outcome is a probability distribution of the set X.
So it's a map from density matrices, the big space of density matrices to the diagonal density matrices, essentially. That's how you're seeing this thing.
It is a map on density matrices on H to probability distribution on X. X and H could be different.
X and H could be different. Okay. I see.
Okay. So I mean, in general, we are considering general measurements of POVMs, right? So X could, the cardinality of X could be larger than the dimension of H.
Yeah, right. Yeah, sure.
So yeah, I won't allow that. So let me say that M will map density.
Wait, that's not how would that be possible? Because how can X number of X be bigger than dimension of H?
No, if you're taking the POVM viewpoint, there's no restriction. All you need are these operators.
But isn't it true that each POVM sort of like each POVM is a positive matrix, right? So it can act on, like, what is the smallest thing it can act on? It can act on one dimension. And each of the POVMs have to add up to identity. Oh, the POVMs can overlap. Oh, okay.
Yeah. I mean, the same MX can appear.
The POVMs can overlap. No, I understand. Okay.
Let's give it a H map to probability distributions. That's what my question is. Okay. So yeah. So M row, M sigma. So what I claim is, this is the thing what Aditya was saying, Hellstrom. So I can look at M row. So this is a probability vector. I can look at M sigma. It's also a probability vector. I can look at what is the L1 distance between them. Okay. So this is less than or equal to the shattered L1 distance between rho and sigma. And also there is an M. There are many M's. There's an M which at its equality. So there's several ways to prove this, but let us take the method which actually proves something slightly more general, which is useful. So actually what I'll show is that, see, this measurement is a special type of quantum operation, right? Quantum operation, you attach an ancilla initialized to 0, do a unitary on the joint system, and then you trace something out. So I would like to show that quantum operations in general cannot increase the trace distance. Okay. So first of all, yeah. So first of all, coming back here, like if I think of these probability distributions as density matrices, they become diagonal density matrices. And the L1, the Schatten L1 norm of a diagonal matrix is nothing but the L1 norm of the diagonal vector. Okay. So in other words, if I were to think of these probability distributions as density matrices, this L1 norm of vectors will be the L1 norm of the density matrix, corresponding density matrices. Okay. So in that sense, there's only one norm that is going on out here. So, but I'll prove the more general claim. E is a quantum operation. So E sends quantum states to quantum states. So what is this telling us? This is actually a type of data processing inequality already. This says that quantum operations cannot increase distinguishability. So as you can see, I mean, the Schatten L1 distance between two density matrices is a notion of the distribution, like norms are notion of distribution. So this says that quantum operations cannot increase the distinguishability. And this is exactly analogous to what we've seen in the classical part of the course, that private coin algorithms cannot increase the distinguishability. So private coin algorithms cannot increase the L1 distance that we started off with. Similarly, quantum operations cannot increase the L1 distance that we started off with. So this is the exact analogous thing. And we saw how that was proved also, right? So first of all, attaching an ancilla does not change anything. Okay, so let us prove it. Very reminiscent of what it is. So attaching ancilla 0 does not change the one norm. Okay. Then like applying unitary. On joint system, doesn't matter. So this does not change L1. So that is easy to check, right? Because let us say I apply the unitary on the matrix. Okay. So all that the unitary is doing is that it's changing the singular vectors. Okay. So in this case, it's changing right singular vectors. So the application of a unitary just changes the singular vectors, but it does not affect the singular values. So the one norm remains the same. The singular values remain the same. This is true whether you apply the unitary on the left or the right. And okay, yeah. So one thing is, maybe I should make it clear out here. What do I mean by applying the unitary on the joint system? So what does it look like in terms of density matrices? So this is the density matrix rho goes to rho tensor ket bra 0. And this is the density matrix rho. I mean, now this rho is on the joint system, of course. It goes to U rho, U inverse. So I mean, when I talk of unitary, okay, I mean, the word unitary denotes a matrix. I mean, it's something that sends a vector to a vector. But now if I want to apply it to a density matrix, this is the definition. So what is this motivated from? Remember, like, so in fact, this brings back to a comment that I made long time back. So remember, rho is a density matrix. So density matrix, it's a Hermitian matrix. So it has an orthonormal basis of eigenvectors, and the positive semi-definiteness says that the eigenvalues are positive, and trace one says they add up to 1. So any density matrix can be written as something like lambda I. Okay, so the V's are the eigenvectors, lambda I's are the eigenvalues. So this notation says that if I just look at, let us say, I equal to 1. So ket V1 bra V1. So that will be the pure state or the rank 1 density matrix, which is normally denoted by the vector V1. Similarly, ket V2 bra V2 is a pure state, normally we just denote it by the vector V2. And remember, the lambdas are like probabilities. So they are positive and they add up to 1. So this notation is saying that a density matrix is nothing but a probability distribution over pure states. So any density matrix is a probability distribution over pure states, and this gives another name for them called mixed states. So mixed states are probability distributions over pure states. Pure states are rank 1 density matrices. So a general density matrix is a mixed state. It's a probability distribution over pure states. So I know how the unitary will act on a vector. It will multiply the ket vector on the left. So Vi will go to U times ket Vi. But now there's a bra. So of course I will take conjugate transpose, and that will put a U conjugate transpose on the right, which is nothing but U inverse. Okay. So that is this, and then trace out ancilla. So that is row AB. We'll go to trace out, let us say, ancilla A. This is what mathematically these things are. Okay. So applying unitary on the joint system does not change the L1 distance. So this is just like the classical thing. Attaching the ancilla did not change the L1 distance. So there the ancilla was ket 0, and there was also the private point, but nevertheless it did not change the L1 distance. Then applying a reversible algorithm, an invertible algorithm, also did not change the L1 distance there. So the only thing that reduced the L1 distance was the discarding operation. So here the only thing that will reduce is the trace out operation. So this is right. So tracing out cannot increase L1 distance. So that's what we have to prove. So this is the only non-trivial thing to prove. And this proof is very easy once we have the alternative characterization. So let's prove this. So let us say M is a matrix on the system A, and I want to trace out A. So I will trace out A. So I'll get what in my notation I'll call A. So now I would like to say that, so the one norm of NB, by definition, well, I mean the alternate characterization is max over V. So this is V on the system V. So this is trace of MV. Right? Now, max of
just to make things, I mean, this doesn't make sense. So inside the mod, you should write trace of MAB VB tensor IA.
What you're saying, the A system I'm only bringing in now.
No, but other, I mean, okay. So I think I skipped this step.
So yeah, so the second equality is one where you should give some thought. Okay, but now this is less than, as you can see. So we will address that, but for now let us believe this equality. So now, this is of course less than a general unitary on the system AB, right? This would have been. So that finishes the proof. That tracing out cannot increase the one norm. So this is the thing. So let's work with the traced out matrix. And this is true for general matrices. Okay. So let us look at the one norm of the matrix M on the system B. So by the alternate characterization, it is max over unitary is V on the system B, trace of MV. And now this is the thing. So, so this is again a property of the partial trace, which you can check out by writing in terms of basis vectors. But it is also, I mean, if you want to abstractly characterize the partial trace, this is one way to do it. So partial trace has this property. Check that trace of MB with respect to any matrix, let us call it P. It doesn't have to be unitary, nothing. So this is equal to trace of MAB, identity A. So this is in fact one way of characterizing the partial trace. Like the partial trace is the unique partial trace. So remember, what is the partial trace doing, right? I mean, the partial trace was sending MAB, the trace out A operation, was sending it to MB. So partial trace is the unique operator which sends matrices on AB to matrices on B, satisfying this property for every arbitrary matrix. So again, I repeat, so partial trace is the unique operator, unique linear operator, so it has to be linear on matrices AB. So it's a linear operator on matrices, which sends matrices on AB to matrices on B, satisfying this identity for all.
Isn't this definition cyclic? Because to define MB, you need to define trace out of A.
No, trace of the operator, let us say, is the sum of the diagonal entries that I've defined.
Okay, okay, I see.
Yeah, and then the partial trace you can be defined from here. So this is one alternate way of characterizing the partial trace. So, but you can go to the basis picture and work it.
No, I wasn't saying that. I was just saying that MB, like the MB that you've written inside the trace MB times rho B or PB. This to define this MB, you have to define the partial trace, but you're defining the partial trace using MB.
Yeah, so
it's cyclic, right?
No. This is just notation. So okay, but let me even address that. So all I'm saying is this. No, that's not an issue. So if you like it, I'll write it this way. So partial trace is the unique linear operator sending matrices MAB to matrices on B, satisfying this property. So now the question is, why should such an operator exist, and why should it be unique if it exists? So these are standard linear algebra questions. I mean, you can answer them abstractly, but anyway, I mean, we have the explicit form. But if you want a basis independent description of partial trace, actually this is the way to go.
So it's like the function if such that g of f of something is equal to g of a bigger thing. That
kind of, see, I mean, you can define the exponential function also that way. No?
Yeah.
The exponential function, I mean, which you call e to the power x, is a unique function from R to R, satisfying
Whose derivative
f
is
of x
equal.
plus y is fx times fy. And
Yeah,
all I require is f of 0 should be 1. That's the
right. I know, I get
whatever.
it.
And f of 1 is something fixed. Yeah. So this is the same kind of thing. Okay. Of course, then the hard part is to show that such functions exist and they're unique and all that. Yeah. So that is true for the exponential function also. That's true for this also. But yeah, I mean, the same thing you can say in a more sophisticated way, but it's basically the same thing that maybe it make it more convincing. So let us look at this. So, okay, this operation, let us say trace of m dagger n is actually inner product on matrices. I take two matrices m and n, okay, and I define their inner product this way. In fact, this should not be a surprise at all. So trace of m dagger n, you can check out what it is. So stretch the matrix into a long vector. So the matrix, let's say, is a k by k matrix. So in row measure order, stretch it into the vector of length k square. So stretch m into a long vector, stretch n into a long vector. Take the usual dot product for vectors, or basically for tuples. Okay, and you can check that it is the same as the left hand side, trace of m dagger. So now all I'm saying is that the right hand side of the above one is this, that it is it's identity A tensor. So yeah, because I did not put a dagger, I put a dagger here. So this is a certain inner product. Okay. And because this inner product, and what is this operator?
This is just a trace of maybe times IA or PB, right?
No, yeah. So this operator. So what am I saying? This, I mean, it's P dagger D mapping to identity on A tensor P dagger. That's the operator I'm talking about. Okay. This is a linear operator on matrices over B. Right?
Yeah.
So
now take that joint.
Yeah, it's a linear operator matrices over B. And this is so in this picture, my k by k matrices are vectors. Okay, and operators on vectors are basically, I mean, send a k by k matrix to some other k by k matrix. So to emphasize that these operators send k by k matrices to k by k matrices, often in the terminology we use super operator. Super operator is just a linear operator acting on the vector space of matrices. Okay. So this operation is a super operator. Okay, fine. Super operator. I mean, this is inner product on matrices. So this should have an adjoint. So I should be able to write just P dagger B out here, and the adjoint of this identity A tensor operator. Okay. And this I should be able to apply on MAB. Okay. So we know that if I have if I have some inner product expression like this and I apply a linear operator on the first vector, I can move the effect of the linear operator to the other coordinate by taking the adjoint. So this is linear operator on k by k matrices, tensor identity, so it should have an adjoint. Okay, just abstractly, and that adjoint is the partial trace.
I mean, you can write the map explicitly. It's the
Yeah, you
adjoint-
can write the map explicitly, but
it's IA tensor IB. It's just IA tensor IB.
IA tensor IB, no. No.
No, no,
No,
as
no,
in as in the adjoint map, right?
this map is the partial trace. Okay, so
Yeah.
of
That map
the-
is the partial. That map is the partial trace. I'm saying the original superoperator that is the thing. That's precisely IA tensor IB, because you operate IA tensor IB and you put some extra ancilla and on A and tensor it with rho B, and you get IA tensor rho P dagger B, whatever. So
No,
your
what you're talking, I mean, this is the original superoperator. Which sends the matrix. Forget the dagger. I mean, the dagger is just there for consistency with this. So it sends a matrix P on the system B into a matrix on the system AB.
Yeah, isn't that so? I mean, can't we write that in closed form as IA tensor IB? The map, I mean. So IA tensor IB acting on PB is IA tensor PB. That's what I was saying.
Yeah, of course. Yeah. Okay, so anyway, so this is a little more abstract viewpoint, but at least this should convince you that I mean, this this abstract beast should exist. Okay, which is what we call the partial trace, because is the adjoint of something which is very explicit and which we know exists. So that would be an abstract definition of partial trace. Okay. Yeah, but I mean, is that okay, Hari?
Yeah.
Yeah, I mean, this is the lesser abstract definition of the partial trace. You can make it even more abstract if you like. The drawback of this lesser abstract definition is it requires the existence of inner products. Okay, but actually trace makes sense even when there is no inner product in the vector space. So partial trace also makes sense when there is no inner product in the vector space. So the more abstract definition works even in that sense. But that's much more abstract to write down. I don't want to write it down. If you I mean, it's a good exercise to work it out on your own once you read the fully abstract definition of the partial trace from, let's say, Lang's algebra or something. Okay, but this one is something that may be useful to us from time to time. So that's okay. Yeah. So this is the second equality, and then of course, if I take general unitaries VAB, then this becomes an inequality, and then this is the one now. So what have I shown? I've shown that tracing out cannot increase the one norm. In general, in fact, it decreases the one norm, and that proves this more general claim. In particular, if I'm doing measurements, I prove this inequality. And the final comment remains that there is an M which attains equality, so that you can easily check. Okay, so look at rho minus sigma. So rho minus sigma is now a Hermitian matrix with trace 0, right? Because rho had trace 1, sigma had trace 1. So the Hermitian matrix is real eigenvalues. So I can write it into the real part. So basically go into the eigenbasis. And this is just the positive part. So this is just rho minus sigma, but restricted to those eigenvectors with positive eigenvalues. Okay, and then there is the negative part. So this is rho minus sigma, but restricted to those eigenvectors with negative eigenvalues. And remember, like this and this are orthogonal, right? I mean, these are like different. This is one bunch of eigenvectors. This is another bunch of eigenvectors. So these are orthogonal. And now I can actually take a two outcome measurement. Okay, so so I can define like M is M plus M minus. So M plus is the
maybe write on a new page. This is getting a little crowded.
This is getting yes. So sigma
So this is another characterization that you're doing, right? This is for specifically for.
No, I want to show that equality can be attained.
Okay. Okay.
Let me write it. Change the setting. So the positive part. This is,
And this is doable because rho minus sigma is a Hermitian matrix, right?
yeah, restricted to positive eigenvectors. So I mean, that is the abuse of notation. This is eigenvectors in positive eigenvalues, and this is restricted to negative eigenvectors. And these have orthogonal support because they are different eigenvectors. Eigenvectors are orthogonal.
So it's like rho minus sigma is Hermitian. That means eigenvalues are real. There are some eigenvalues which are positive, some which are 0, some which are negative. You're grouping the non-negative guys together, calling that rho minus sigma plus, and the other guy you're calling rho minus sigma minus.
Yeah.
And
Yeah,
rho
the
minus sigma
zeros you
minus,
can put in either one if you want.
right. And this rho minus sigma minus is itself matrix with positive eigenvalues, but to turn them negative, you're putting the minus in front.
Yeah. So now M plus is the projection onto positive eigenvectors. And M minus is the corresponding projection onto negative eigenvectors. Okay. So my measurement operator is M plus M minus, just two outcome measurements. Okay. And now if I look at
so we need to just verify this, right? The M plus M minus is identity on the rho minus sigma support space.
Yeah. So what is this? This is.
I'm just saying some things because maybe Hari, I think you're going a little fast for a newcomer. You're going really fast. I'm sorry.
Yeah, maybe I should repeat it next time. I'll repeat it next time. So trace M plus rho, trace M minus sigma. Sorry, trace M minus rho. This is the probability distribution of first guy. Trace M plus sigma. Trace. So it's a two outcome measurement. So the probability vector has just support of size 2. So this is. So what is this? This is trace of M plus rho minus trace of M plus sigma. Well, yeah, I mean, there's a linear trace, so I can even write this.
So equality is because of orthogonality, and then
no orthogonality. This is just I'm writing down what is the one norm of a vector of size 2.
Okay. So this a trace of M plus rho is the probability on the positive. I see.
Okay. So this is trace of M plus rho minus sigma. Okay. Even now the mods are there. Trace of M minus rho minus sigma. Right? But M plus rho minus sigma
is equal to.
Okay, is basically the what? Sorry,
these two traces are the same. That's
it. Also happens with sum of positive eigenvalues of rho minus sigma. Okay. And this one is like sum of absolute values. Remember, like, I mean, I put a minus here to move the overall. I put a minus here to move the overall sign out. So sum of absolute values of negative eigenvalues of rho minus sigma. But remember, rho minus sigma is a Hermitian matrix. Right, so the single values are anyway the absolute values of the eigenvalues. So that's exactly what I've done. So this is the this is the
one norm.
Yeah, so this is the one norm of rho minus sigma. So this is the sum of absolute values of positive eigenvalues of rho minus sigma, sum of absolute values of negative eigenvalues of rho minus sigma. So in other words, this is the sum of all the singular values taken together, rho minus sigma. So this is rho minus sigma. Okay. So actually, I mean, this special two outcome measurement, which projects where the outcome plus projects onto the negative, projects onto the positive eigenvalues of rho minus sigma, and the outcome minus projects on the negative eigenvalues of rho minus sigma. That I mean, those projection operators, okay, and overall the span of those two subspaces is the entire space, right? I mean, eigenvalue is either positive or negative. Let us say I plug in 0 in one of them, doesn't matter. So yeah, so it's a certain two outcome measurement, and I can write down what is the probability distribution for this two outcome measurement for rho or for sigma, and then I can calculate what is the L1 distance between them. So these are probability vectors of size 2 coordinates. I can just write it down and get this. So anyway, I think it's a little fast, so we will revise some of it again in the next lecture. Questions, right? If not, we'll stop now and then see you on Thursday.